Today we are going to once again cover problem set 5. It'll be a little bit of a review from last week, so bear with me. First, we are going to install the dplyr library, and then we're going to run the library. I had already installed it beforehand, and again, you can check whether it's successfully installed by just running it a bunch of times, and if it comes back blue, you know it's worked. Moving on to problem 1a, I covered this, I believe, last week, and I showed you that you need to find the sample size and then the x for whatever it is that you're trying to find. So in our case, it's all babies that tested negative. So it'll be the total number in the sample that we have here, and then subtracted by those cases that were not positive HIV. So again, you have to change these numbers in the assignment in order to get the correct answer. So when we run this, we are just saving these as objects here. You can see there. And then we can do these calculations by just running this code. And you'll see that this P is just simply the X divided by the N, which is 95%. And then, as I showed last week again, we can just C-bind that all together, and then you'll see that those objects that we have saved can actually be put into a table. So that's what C-bind does. And then now we have the sufficient information to actually go ahead and make that standard error calculation in 1B here. And we're just following this formula. So it's just P and then multiplied by 1 minus P over N. And so we have both N and P that we just created. So we should be able to just copy this code and calculate the standard error. Now on your end, as long as these two numbers are changed correctly, then you should be able to not have to do any manipulation in 1B, and it will just spit out the correct standard error right there. And now we can calculate the confidence intervals in 1C. And again, just using this formula. So we can simply take the Z, and then we can add and subtract that from the P that we created by multiplying Z times the standard error. And that is our answer. So moving on to 1E, I'm just showing you how you can create a table if necessary to present your answers. So you use the matrix function and you specify the number of rows and number of columns, and then the information that you want, actually the values that you want in that matrix. And so when I run this, you'll see that 151, it's 151, 13, 120, and 40. So that's how it spits it out. So now we have created a table, and we can add a column to that table by using the cbind function. So there's two ways we could do that. We could use the cbind function with another list. So we can use the cbind function, and then we'd have another list simply added on as another row because it's a column bind. R bind would be another row. Doesn't look like that example worked, but yeah. So if you did R bind, it would add it as a row, and if you did C bind, it would add it as a column, as you can see in there. But what I want to actually do is just get the row sums. So the row sums This is actually a function that calculates the row sums of each row in a certain table. So I'm just passing in this table that we made. So it'll just add up 151 plus 120 and then 13 plus 40. And sure enough, that's what happened. And so now we have that output. We can actually just put that in the cbind function, and it will now give us an updated table. If we want to overwrite that table, we can just set it equal to that table's name, and then it will have that updated column. And if we wanted to change the column names, we just use the column name function, call names on that table, and then we put in what we want the column names to be. And then now we kind of have a nicer looking table. And obviously we can add rows, as I just showed previously, and we can add row names. So that's what this example is showing. So it's just adding the column sums this time. So the column sums, if you were just to look at it, it would just add it up and give us it back in row format. And then we're just going to rbind that. So rbind, again, just adds the rows. And then we're going to use the row names function to label. And so now you can see we have a properly labeled table. Now let's cover 1G. So 1G and this first part are actually similar, so let's just do 1G first. We want to see if there's a difference between the number of, the sample, of negative bursts of HIV between the treatment and control groups. And so this prop.test function essentially carries out this formula here. And so we enter in the number of negative tests for the treatment and control groups over the total number of people in the treatment and control groups. And so we just enter this in and we run it, and you'll see that you can find this p-value here. And so we can reject the null hypothesis because this p-value is so small. It's 0.000327. This is scientific formula. And so that means that there's evidence that there's some difference between the treatment and control group, some statistical difference that is significant between the treatment and control groups in terms of the proportion of those testing negative. So again, that's covered here in this by accident as well. And so I'm just going to again show you how you can kind of present it a little bit nicer. You can again use this matrix table into A. Let's clear this out. Give ourselves a little more space. And you can see that that prints out the matrix. And now that we have this matrix with the relevant outputs, we can actually use the chi-squared test, or chi-squared test, and this helps us understand expected values. And so if we copy this and put in that table 2.1 into the chi-squared test, and we put the $ expected, then it will give us the expected values for each column and row. And so that's the expected values. because we put on the $ expected, and we can just get the test by just removing that expected value. And when we run it, we should get the p-value, and so that will give us the answer. If it's statistically significant, we have evidence that there is evidence that the expected values are different from our observed values. So now moving down to problem 3. We have recorded values, some observations of something that occurs on Fridays. So this could be, traffic, the number of cars. It could be the number of students going to school, anything. This is just an example. And if these are our observations, we can save it as a list. And now we can use this chi-squared test. Again, we're going to do the same thing. We're going to put the list into the chi-squared test, and you have to have this correct equals to false. And then we'll put the $ in expected. And if there was kind of an even chance of this occurring without any type of pattern, of course, it's a very simple example, but we would expect that whatever it is that we're measuring would be the same across all Fridays. So that's what the expected value is essentially just this added up and then divided by 3, and then evenly spread out across each day would be 310, 312,000, as you can see there below. And so if the probabilities we can set the probabilities in a separate list if we believe that all probabilities were equal, so that, in other words, there's a third chance of something happening on each day, kind of evenly spread out. And so once the probabilities have been saved, we can use that chi-squared dot test function and input those probabilities, and then we can see whether there is significant difference in our observed values from what we expected. And it looks like our p-value is, again, extremely small. So there is not kind of an equal chance of whatever phenomenon that we were witnessing on Fridays. There's not an equal chance of it occurring. There's some pattern. There's something going on there. And so this is similar to 2D and 2C as well as 2A from your problem set. So you're going to, I think, have to possibly change some of this around in order to get the correct answer. So our last part that I want to show you is we're going to download some DTA data from this website, and then we're going to save that as the URL, and we need to use the foreign library in order to read this file because it's a DTA, it's a stata file. So I'm saving this URL. I could also just put this into the read DTA function. It would still read it, but I'm breaking it up just to make it a little bit easier. And so now I read that in, and it looks like that successfully worked. And so now we have this, well, let's go back to that. We have birth weight based on family income, the birth weight, father's education, mother's education, and a number of other demographic variables. And so what we're going to do is first we're going to plot the relationship between the number of cigarettes smoked, which is called the SIGS column, and birth weight. And if we wanted to put the best fit line, the regression line in there, all we'd have to do is put in LM, birth weight, and SIGS with the cigarettes as the regressor or the explainer variable, explanatory variable, and the birth weight as the dependent variable. And so if I run that together, then we can see that best fit line, which you can see here as well. Then we can kind of run the regression. What should we take away from that graph? Well, we can see that there does seem to be some relationship between the baby's birth weight and the number of cigarettes. It's kind of downward sloping, which suggests that perhaps the more cigarettes one smokes, the lighter one's baby will be. So we can kind of test that more formally by looking at this regression that we kind of ran here. And we're going to save it. Without using the summary function, though, in the regression, we can only see the coefficients. So if you wanted to see a summary table with some t and p-values, you would use the summary function. And then we get the standard error, t-value, r squared, p-value, and other information. But let's just say we want to extract the coefficients only. We can do that by using the $sign and typing in coefficients from the regression list that we have saved here. So those coefficients come out as follows. And so what this is telling us is that when a mother smokes 0 cigarettes, the baby is on average 119. I think maybe this is kilograms or something. And then that's the birth rate. But as the mother smokes more cigarettes, so an additional 1 cigarette a day would decrease the baby's weight by 0.51. So if we wanted to try to calculate what a baby's weight would be based on how many cigarettes the mother has smoked, we can actually do that by using those coefficients that I've just saved in this coefficients list. So I'm taking the first coefficient. So this is just the way you select data from a list. C1 will select the first element and C2 will select the second element. So I'm just selecting it, and then I'm converting it to this format called double, and using the as double function in order to convert it to that. So now I have beta 0. I could have just also typed in beta 0, 119.77. These are equivalent. This is just a fancy way to do it. Same thing for beta 2. I could just type in negative 0.51. So now I have that saved. And now we essentially can make a formula. So that formula, we can set the number of cigarettes that a person might smoke a day, and then that will be saved as an object, and then I will take the beta 0, so 119, plus the number of cigs smoked a day, which would be multiplied by that beta 1 coefficient. So if we did this, we can say that a mother who smokes 10 cigarettes a day, all else being equal, will have a child that is 114 kilograms, or whatever the measure is. And as you can see, like as the number of cigarettes goes up, the weight obviously keeps going down, and it goes down in a linear fashion, which is why it's called a linear regression. It goes down by the same margin. 0.51 for each cigarette that's added, right? So if I did 31 cigarettes instead of 30, it would be what? It would be 103.96. And so you can play around with this to understand kind of the intuition of how a regression works and the information that it can tell us. Again, as you can see up here, the relationship, it might exist, but there's a lot of observation. So this is just kind of a general rule of thumb. Obviously, there's not an extremely tight relationship. If we saw an extremely tight relationship, we would see like more of a 45-degree angle or some type of tighter angle between the observations. And so that's, again, why it's also important to graph something before you regress it.